Okay, we're recording. Can everybody see the screen? Will we go over homework? Oh, anyone, if you have any homework questions, yeah, go ahead. We can go over homework. All right. Do you have any questions you want to go over now? Yeah, sure. Section 2.4, number 15. Give me a sec. Homework. I haven't posted homework for a while. I posted one today. I don't know if anyone had any chance to do it yet. Let me give everybody, for 2.4, let me give the other people a chance to do that. Maybe we'll go over that next time. All right. Yeah. Okay, so take a chance, take a stab at it. Try and do number 15, and we can go over that one next time. Let's give some people some time to do it. Okay. All right. Any other questions? Okay. Okay, so let's review what we did last time. We were in section 2.4. We were discussing sequences. Okay, so we said a sequence is an ordered list, denoted like this, A sub n in braces. That denotes the entire list. If I want to refer to individual terms of the sequence, I just write A sub n. Okay, and we like to have an explicit formula for A sub n. Okay, so we talked about having an explicit or closed formula for a sequence. We also discussed geometric progressions. Okay, so that was a special type of sequence where each term of the sequence A sub n is equal to A times R to the n. Okay, where A was the initial term, R was the common ratio, and n was greater than or equal to 0. Okay. All right, so basically a geometric progression is any sequence that starts with some real number, and then I am multiplying by the same number over and over again to get each successive term of the sequence. Okay. We also discussed an arithmetic progression. All right, an arithmetic progression was of the form A plus n times d. Again, A is called the initial term. D, we said, is called the common difference. And again, n starts at 0 usually in an arithmetic progression. Okay. All right, so here again, we're starting with an initial term A, and this time to get to the next term, we just add d. And then to get the next one, we add d again, and we keep adding d to get all the terms of the sequence. Okay. So those were two special types of sequences. We also discussed a recurrence relation. So a recurrence relation was just another way of describing the terms of a sequence. Okay, it's another way to specify a sequence. Okay, and a recurrence relation is an equation where each term of the sequence is defined based on the previous terms of the sequence. And I also would have to give you some initial conditions, right? I have to tell you where to start. Okay. Remember, we also said that if you're given a recurrence relation, it's always nice to find a solution to a recurrence relation. Solutions to recurrence relations. Right, and what is a solution to a recurrence relation? That is an explicit or closed formula for the sequence that fits with the recurrence relation. Okay, so it's an explicit formula that gives us the same sequence as the recurrence relation. Right, and then the last thing we discussed was the Fibonacci sequence. Okay, which is a very famous sequence just because it appears a lot in the natural sciences and in natural phenomena. Okay. All right, so any questions on any of that stuff from last time? Okay. All right, so if there's no questions, we're going to now continue in section 2.4. Today we're going to discuss summations. Okay, so we're going to discuss summations and something called sigma notation. This is a topic which I'm sure most of you, if not all of you, have seen before in some capacity. Okay. All right, so a summation is basically, or sigma notation is used to shortcut adding the terms of a sequence together. So if we have the terms of a sequence and we want to add those terms together, all of them or some of them, we indicate that using summations. Okay. All right. So we use summations and sigma notation to add together the terms of a sequence. Okay. Okay, so the notation is as follows. All right, we start with a capital letter sigma, which is, this is a Greek letter sigma. It's a Greek S, a Greek capital S. Okay, it's called a sigma. So this is a sigma. Okay. All right. So this big sigma here represents the word sum. It means sum or add. Okay. Next to it, I write a sub j, where a sub j represents the terms of some sequence, a sub n. Okay. And then on the bottom here, I'm going to write j equals m, and on the top, I'm going to write n. Okay. Now j equals m and the n, m and n are going to be integers, all right, with n greater than or equal to m, all right. Those two numbers, j equals m and the n, are going to be called the index of summation, all right. So j is called the index of summation. Okay, m will be the lower limit. And n is the upper limit. Okay. All right, so those are the names of all these things. Now, what does this mean? If we've got some sequence, a sub n, this thing is telling us to add up certain terms of that sequence. Which terms? Well, it says start by plugging in the lower number m for j. So if I plug in m for j, I get a sub n. Okay. Then add to that the next term of the sequence. What would the next term of my sequence be? A sub m plus 1. Then add the next term of the sequence, which would be a sub m plus 2. And then keep adding up the terms of the sequence until you get to the upper limit n. So you keep adding until you get to a sub n. Okay. So this sum of a sub j from j equals m to n means to add up all the terms of my sequence from a sub n up to and including a sub n. Okay. Is n always greater than or equal to m? Yes. Okay. So let's write that down here. All right. N will be greater than or equal to m, where n and m are both integers. Okay. All right. So again, this means this is, so let me write this over here. This is the sum from j equals m to j equals n. So I'm starting by plugging in m for j, and I'm adding 1 each time to m until I get to n of a sub j. Okay. All right, so this is the notation that's used. This is what it means. Okay. So let me show you, if you're not familiar with this notation, let me show you what it means through an example. I think that's the easiest way to see it. Okay. All right. Let's say I have some sequence a sub n, where the terms of my sequence a sub n are determined by the formula, let's say, n squared. Okay. All right. So let's say I want to add up a couple of the terms of this sequence. Well, let's say I'm starting. Let's say this sequence starts from n greater than or equal to 0, right? So I want to add up a couple of terms of this sequence. So let me write out first what the first few terms are. A0 would be 0, A1 would be 1, A2 would be 2. All right, one moment. One second. Okay. A2 would be 2 squared, which would be 4, and so on and so forth. Okay. If I write the sum from j equals, let's say, 0 to 3, okay, of this sequence, so of n squared. Excuse me. I'm going to write it as j squared. So the sum from j equals 0 to 3 of j squared. This means I want you to plug in 0 for j. So I'm going to start by plugging in 0 for j. So I would get 0 squared. Okay. Then I want you to do the next term of the sequence. So if after 0, I have to plug in 1. I would get 1 squared. Plus, then I go to the next integer, 2. That's 2 squared. Plus the next integer would be 3. That's 3 squared. And I stop when I reach n, when I reach 3. Okay, when I reach the number on top. Okay. So this is equal to 0 plus 1 plus 4 plus 9, which is 14. Okay, so this sum is equal to 14. All right. Okay, any questions on that? Okay. What is 3 again? That would be the 3. Yeah, 3 is the upper limit. So meaning I start by plugging in the number down here for j, right? So I start by plugging in this number, 0 for j. So from j squared, it becomes 0 squared. Each time now, I'm going to increase that number by 1 until I get to the number on top. Okay? So if I started at 0, Next I add 1 to that, and I get 1 squared. Then I increase that by 1 again, I get to 2 squared. I increase that again, I get to 3 squared. And then I stop when I get to 3 because that's the number on top. Okay, so the number on the bottom, the lower limit, tells me where to start. And then I keep going through through all the integers until I get to the number on top, until I get to the upper limit. Okay. All right, let's try another example. Let's say I asked you to evaluate this sum. Let's say the sum from j equals 0 to 3 of 1 over j. Okay, so 1 over j represents the terms of a sequence. I want you to add the terms of this sequence starting from j equals 0. Oh, excuse me. I meant from j equals 1. Starting from j equals 1 and going to j equals 3. Okay, so this time I'm starting from 1. So if I plug in 1 for j, I get 1 over 1 plus, now next I have to plug in 2 for j, so I get 1 over 2. Plus then I plug in 3 for j, I get 1 over 3. So this is equal to 1 plus a half plus a third. Okay, so if I wanted to add that up, I'd have to have a common denominator for all of these. So this is the same thing as 6 over 6 plus 3 over 6 plus 2 over 6, which is 11 over 6. All right, so this sum equals to 11 over 6. Right, and that one was 14. All right. I can start my bottom number at any number I want, really, and I can end at any one number I want, okay? Another thing I want to point out is I don't have to use a J. I can really use any letter that I want. So if I want, I could use a K or an I. Really, I, J, and K are the 3 most commonly used letters. All right, so I could write, what is the sum from K equals, let's say, what is K from K equals 4 to 10 of negative 1 to the power of k. Okay. What would that be? So if I'm starting by plugging in 4 for k, this is going to be negative 1 to the 4th, plus negative 1 to the 5th. I keep going up, k keeps going up by 1 until I get to 10, plus negative 1 to the 6th, plus negative 1 to the 7th, plus negative 1 to the 8th, plus negative 1 to the 9th, plus negative 1 to the 10th. Okay. Now, negative 1 to any even power will be 1, and negative 1 to any odd power will be negative 1. So this is 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. So 1 and 1 cancels, that's 0. 1 and 1 cancels, that's 0. 1 and 1 cancels, so that's 0. I'm left with 1. So this thing would be equal to 1. Okay. All right, so any questions on that so far? Okay. All right. Now, sometimes it's useful to shift the index of summation. All right, so I can keep my sum the same, but sometimes I want to shift the index. Okay, but to compensate for that, I'm going to have to change the expression a sub j or a sub k, whatever my letter is. Okay, so let me demonstrate that with an example. So sometimes it's useful to change the index of summation. Okay. So for example, let's say I have a sum from j equals 1 to 5 of j squared. Okay. But for whatever reason, let's say instead of starting at j equals 1, for whatever reason, I want to write this expression starting from j equals 0. Okay. I can do that. I can rewrite this as starting from j equals 0. All right. But now I have to compensate for that. If I'm starting from 0, I'm going to also have to end at 4 now. So just like the 1 went down by 1, the 5 has to go down by 1. Okay. And to finish compensating, because I went down by 1 at the index, by the expression itself, I have to go up by 1. So here, this has to go up by 1, j plus 1 squared. Okay, so whatever amount I go down by or up by in the index of summation, I have to do the reverse with the expression that I'm adding, okay, that I'm summing. Okay, and let's check to make sure that these two things are equal. Okay, so if you look at this sum here, this sum is going to be start with plugging in 1 for j. You would get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And here, if I start by plugging in 0 for j, I get 0 plus 1, which is 1 squared and plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, so you see that they're equal. All right, so whatever amount we increase or decrease j by, we need to do the opposite for a sub j. Okay. No, we would only do this for adding and subtracting. I wouldn't do it for multiplying. Okay. Okay, by index of summation, I mean the j at the bottom, those two numbers, the j at the bottom and the top. So in other words, I mean, I'm referring to this. Okay, okay. Yj plus 1 squared is, oh, so that's what I'm telling you. If you want, sometimes you want to change your index. So for this example, let's say for whatever reason, instead of starting at j equals 1, I want to start at j equals 0. But I want to make sure that sum is the same. I don't want it to change. I want it to be equal. So I can change it from 1 to 0. I just also have to change 5 to 4. I have to go down by 1. And in here, I have to go up by 1 so that it stays equal. So the two sides are equal. They're the same. Okay, so I can change the index of summation, but to keep my summation the same, I have to balance it out. All right. Okay. Oh, sometimes it's useful. Sometimes it happens that is useful. Okay. One example would be, let's say you want to use a summation formula. We'll get to summation formulas soon. So summation formulas a lot of times require you to start your index at a certain number, like j equals 0 or j equals 1. Okay, so you might need to adjust to get to that. Okay. Another example could be, let's say, if you have two different sums that you want to add together. To add them together, they would have to have the same index. Okay. Okay. So sums of sequences appear a lot, especially if you do if you end up doing infinite series in calculus. You'll see summations a lot. We're going to do some summation formulas, okay, which are basically formulas that are shortcuts to tell us what certain sums equal to. Okay, we're going to start with a summation formula for a geometric progression. All right. All right. So I'm going to give you a formula for a summation formula for a geometric progression. Okay, and geometric progressions, by the way, are also sometimes called geometric series. I think we maybe have mentioned this a little bit last time, right? In calculus, as I said, you see geometric series where that's an infinite sum. Okay. All right. So here is the summation formula for the terms of a geometric progression. All right. So if A and R are real numbers, right? So your initial term and your common ratio are real numbers, and R does not equal to 0, then the sum from j equals 0 to n of AR to the power of j, okay, So this is, I'm adding the terms of a geometric progression, right? AR to the J, it's a J instead of an N, right? Will equal to. So instead of sitting there and having to add up all the terms, what we're going to do is we can use this formula to give us a shortcut for the sum. Okay. So if anytime I want to add up the terms of a geometric sequence or geometric progression, ARJ, starting from J equals 0 and going to some number n, it's equal to A times R to the n plus 1 minus A divided by R minus 1. Okay, as long as R is not equal to 1. And if R is equal to 1, then the sum is just n plus 1 times A. Okay. Okay, so this is a shortcut for adding up the terms of a geometric progression. And let me show you an example of how this would work. All right. Let's say I asked you to evaluate the sum from J equals 0 to 5, okay, of 3 times 2 to the power of J. Okay, so 3 times 2 to the J, that's a geometric progression. Okay, it has an initial term A, which is 3, a common ratio R, which is 2. Okay, so here R is not equal to 1. All right, so I'm going to use the first formula here. Okay. All right, so instead of sitting here and adding all the terms, so if I wanted to sit and add all the terms, I would have to do 3 times 2 to the 0 plus 3 times 2 to the 1 plus 3 times 2 squared plus dot, 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 all the way up to 3 times 2 to the 5th. I would have to evaluate all of those and add them up. What the summation formula does is it allows me to skip all of that addition. It tells me that this sum is equal to A times R to the n plus 1. So that's 3 times 2. N here is 5. Let me write that out. N is 5. So to the 5 plus 1 minus A, so minus 3, over R minus 1. So over 2 minus 1. Okay. So I took A, R, and N and plugged them into this formula. And that gives me what the sum equals to directly without having to sit there and add up all the terms. Okay, so if I evaluate this thing, this is just going to be 3 times 2 to the power of 6 minus 3 over 1. So I don't even have to write that. 2 to the power of 6 is what? What's 2 to the power of 6?
$64.
Yep, thank you. Thank you. You guys are all you guys are all my computer science people, so you should know powers of 2 pretty well, I would hope. 3 times 64 minus 3, which is equal to 3 times 64 is what? 190 what? 192, yep, exactly. So 192. That's 192 minus 3, which is 189. Okay. So much faster, much more efficient for evaluating the sum to use the formula than to sit there and add up all the terms. Okay. There's much less time involved. Yes.
Sir, when I learned this as A 1 minus R to the power n by 1 minus R, not n plus 1. Is it because we are considering J equal to 0, and in my formula we use J equal to 1 as the beginning?
Yes. Yeah. That sounds right. Yeah.
Thank you.
Okay. So again, because you basically had to have what you're basically talking about what I was referring to just a moment ago, where your formula that you've seen previously had a different index. So if you would change the index of summation, you have to adjust the formula as well. So if you add one, you have to subtract one. If you subtract one, you have to add one.
I understand. So thank you.
No problem. Thank you. Okay. Okay. You can also have something called double summation. All right. A double summation is basically where we have two sigmas with two different indices. Okay. So, for example, you could have a double sum that looks something like this. The sum from I equals 1 to 4 of the sum from j equals 1 to 3 of I times j. Okay. So this would be a double sum. All right. You could think of it as a sum of a sum. Okay. Right. So if you want, you could think of it like this. All right. And again, I'm using two different indices for the index of summation. I've got an I and a j. All right. So how do we evaluate something like this, a double sum? To evaluate it, you first do the inner sum, or the sum on the right, and then you do the outer sum, or the one on the left. Okay. So first, evaluate the inner sum. Okay. So if I do that, let me rewrite it over here. The sum from I equals 1 to 4 of the sum from j equals 1 to 3 of I times j. Okay. That's going to be the sum from I equals 1 to 4 of. Okay. So I'm taking the sum from j equals 1 to 3 of I times j. I'm going to start by plugging in the numbers for j. All right. So I'm starting by plugging in 1 for j. If I plug in 1 for j, I'm going to get I times 1 plus. Next, I'm going to plug in 2 for j. I'll get 2. Excuse me, I'll get I times 2. Then I plug in 3 for j. I get I times 3. So notice that the I is not yet changing. I'm not doing anything with the I. The I so far is remaining as an I. It's just j that's changing first. Okay, and I go from j equals 1 up to j equals 3. And I stop with the first sum. Okay, so that's going to be the first sum. Let's simplify that first sum by adding up all of those terms. So this is going to be the sum from I equals 1 to 4 of, that's 1i plus 2i plus 3i, which altogether is 6i. Okay, so I'll even get rid of the parentheses. I don't need them anymore. I'll just write it as 6i. Once the first sum is done, evaluate the second sum. So now evaluate the second sum. Okay. So now the second sum is going to be, I plug in the numbers for I. So this is going to be 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4. Okay. 4 and 3 is 7. Plus 2 is 9. Plus 1 is 10. So that's 6 times 10, which is 60. Okay, so this sum equals 60. Any questions on that? Okay. So I'm now going to give you a couple of other summation formulas that are used a lot. If you've done calculus, especially integral calculus, you will have seen several of these. Okay. Will you give us the formulas, or do we have to memorize them? I'm going to ask you to memorize them. All right, there's not going to be that many that I'm going to give you. So I'm going to ask you to memorize them. Okay. All right. So we've already done one summation formula. I'm not going to write it again. That was the one for geometric progressions. The next one I'm going to give you is as follows. So I'll write this as number 1 on this list. That also is a summation formula, geometric progression one that I gave you. So maybe I'll let me add it to the list again. Well, no, I'm not going to rewrite it. All right, that's a summation formula you need to know, but I'm not going to put it again on the list. Okay, you have it above. Okay. Oh, this is for a bunch of different sequences. They don't have any special names. Okay. All right, as you'll see as we write them. Okay. So the first one I'm going to give you is the sum from k equals 1 to n of k. All right. The summation formula for this is, well, does anyone know what it is? Does anyone remember? Anyone familiar with it? Does anyone know what the formula is for this? Not n times k, no. Okay. So this is equal to n times n plus 1 divided by 2. Okay. Well, what is this? This is actually the sum of the first n positive integers. All right, let me write it out over here. What is this sum? If I start by plugging in 1 for k, I get 1. Plus, then if I plug in the next one, I plug in 2 for k, I get 2. Then plus 3, plus 4, plus dot, 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 all the way up to n. So this is the sum. This is the sum of the first n positive integers. Okay, it's the sum of the integers from 1 through n. So that sum is actually just equal to n times n plus 1 divided by 2. So you don't have to sit there adding them all up. You can just use the summation formula. So for example, let's say I asked you what is the sum from k equals 1 to 100 of k. Okay. So here n equals 100. So I just plug in 100 into the formula. I plug in 100 for n, I get 100 times 100 plus 1 divided by 2. That's 100 times 101 over 2. 100 over 2 is 50, so it's 50 times 101. Multiply that, you get 5,050. Okay, so this sum equals 5,050. I can figure it out relatively quickly. I don't have to sit there adding the numbers from 1 to 100. Okay. There's actually a little bit of a story behind this formula. There was a famous mathematician named Gauss who lived, roughly 200-300 years ago. When he was a child in school, in elementary school, the teacher gave the kids an assignment to add up the numbers from 1 to 100. So all the other kids sat there adding up the numbers from 1 to 100. Gauss sort of figured out this formula and did it much quicker. And then went and did his finger painting or whatever he did in elementary school. Yeah, it's a famous story. The method he actually figured out to add up the numbers was as follows. Maybe I'll just demonstrate it briefly. Gauss figured as follows. Let's say I want to add up the following numbers, 1 through 100, right? So plus 98, 99, 100. Yeah, I believe it's a true story. Okay. So what he did was he realized the following. He said, let's say I add up the extreme numbers here, the endpoints, 1 and 100. If I add 1 plus 100, what do I get? I get 101. Then he said, okay, what if I add the next 2 in? So 2 plus 99, what do I get? 101. And then if I add the next 2 in, 3 and 98, what do I get? 101. So each time we move in, the sum is always 101. So once you realize that, you just have to ask yourself, how many pairs of 101, how many 101s do I have? Well, if I've got the numbers 1 through 100, I'm going to have 50 of them. So it's just 50 times 101, which is 5,050. And that's sort of, that's basically how we did it. Yeah. All right, nice quote. Yeah, all right. In mathematics and in computers, also in computer science and programming, one of the things that's very much appreciated is efficiency. Okay, can you find a faster, easier way to do something that uses the least amount of calculation possible, right? So the more you can do that, the better you'll be. This was by Gauss, was his name, Gauss, Gauss. All right, so that was the first formula. Let me now move on to the second formula. Okay. The second formula is the sum from k equals 1 to n of k squared. All right, so the sum of the perfect squares, right? 1 squared plus 2 squared plus 3 squared and so on up to n squared. Right? The formula for this is n times n plus 1 times 2n plus 1 divided by 6. Right? So if I asked you, what is the sum from k equals 1 to 10 of k squared using this formula? Since n equals 10 here, you would tell me that this equals to 10 times 10 plus 1 times 2 times 10 plus 1 over 6. Right, that's 10 times 11 times 21 over 6. Okay. The 6 will cancel with the 10, leaving a 5 on top and a 2 on the bottom. The 2 will excuse me. Is that what I wanted? 1 second. Yeah, the 6 will cancel with the 10, leaving a 5 on top and a 3 on the bottom, excuse me. And the 3 will cancel with the 21, leaving a 7 on top. So I'm left with 5 times 11 times 7. 5 times 11 times 7. 5 times 11 would be 55. 55 times 7 would be 385. Okay. The next formula that I want to give you is the sum from k equals 1 to n of k cubed, right? So that's the cubes. So 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. And notice, by the way, for all three of the formulas that I've given you on this list, numbers 1, 2, and 3, you have to start at k equals 1 for this to work, okay? All right, so this sum is equal to the same one as the sum of k, but squared. So this is equal to n squared times n plus 1 squared over 2 squared, which is 4. All right, so if I asked you, what is the sum from k equals 1 to 4? Well, I don't know. There we go. From k equals 1 to 4 of k cubed. Okay, using this formula, it would be, where here n is 4, so that would be 4 squared plus, 4 squared times 4 plus 1 squared over 4. So that's 16 times 4 plus 1 is 5 squared is 25 over 4. 16 over 4, that's 4 times 25, which is 100. Okay. All right, so those are the summation formulas that you need to know. These three plus the one from before, the geometric progression one. I'm now going to give you 2 more that you don't need to know. I just want to show you them because you'll see them again in calculus if you do infinite series. And if you've done this calculus already, then you've seen these 2 already. Okay, so and so the next 2, I'm not going to require you to know. I want to show them to you in case you guys go on to do calculus, or you're going to plan to do 143 or 152. You'll eventually see these. Okay. All right. So number 4, again and again, you don't have to know these 2. I want to show them to you. So number 4, the sum from k equals 0 to infinity. So this would be an infinite sum, which is known as a series. Okay. Of x to the power of k. Okay, where the absolute value of x is less than 1. So x is some number between -1 and 1. Okay. This is equal to 1 over, does anyone know? Has anyone seen this series before? What is it? 1 over what? You took 143. Do you remember what this sum is? Yeah. Except here it's x. So 1 over 1 minus x. All right. And the next one I want to show you is the sum from k equals 1 to infinity of k times x to the k minus 1, where the absolute value of x is less than 1. Again, an infinite sum here, so this is a series. This one is equal to 1 over 1 minus x squared. Okay. And for those of you who have done calculus, you'll notice that the second is the derivative of the first. Okay. All right, so these two you don't have to know. You don't need to know, but they're used in calculus. Okay, the first three are also used in calculus. If you've taken 142 or 151, you will have seen the first three before. When you do the definition of the integral as the limit of a Riemann sum, you'll have seen that. Okay. Okay. Just out of curiosity, how many people here have done integral calculus? That's absolute value, yeah. For formula 2, you only use it when n squared? Yes. For number 2, yeah. That's... Well, that was k when k squared. It was k squared, not n squared. Okay. Yeah, 141, 142 or 151. Okay, so... All right. Yeah, all right. How many people have done 152 or 143 or in the middle of it or going to do 152, 143? Okay. All right. All right. Okay. All right. So then if you have done it or you're going to do it, you'll see these summation formulas again. Okay. All right. Okay. So let's say I ask you the following. All right. Let's say I ask you, what is the sum from k equals 10 to, let's say 100, okay, of k? Yeah. Okay. How would you evaluate this? The sum from k equals 10 to 100 of k. Now, I'm going to scroll back up for a moment. If I want to use the summation formula for this, if I go back to number 1 here, okay, I want to use the summation formula. The only issue is that to use the summation formula, I have to start at k equals 1, not k equals 10, okay? So what am I going to do? I can't change the index, because if I change the index, then I won't have a k here. I'll have a k plus 10, and it has to be a k there, all right? So what we can do, something else that we can do is as follows. This thing will be equal to the sum from k equals 1 to 100 of k, okay? But if I do that, that's too much. I've added the numbers 1 through 9, and I don't want that. I want to start at 10. So what I can do is I can actually subtract off those numbers now. So I can subtract the sum from k equals 1 to 9 of k, all right? So now I've rewritten this as a difference here, where this one has too much, all right? It's got the numbers 1 through 9 in it, and I don't want those numbers, so I'm subtracting them off here. And by rewriting it like this, now both formulas here start from 1, both sums start from 1, and I can now use the summation formula, okay, for both. So this would be equal to, for the first one, it's going to be n times n plus 1 over 2. Remember, it's n times n plus 1 over 2 for both of them. So for this one, n is 100. For this one, n is 9. So this is going to be 100 times 101 over 2, like we had before, minus 9 times 10 over 2, right? 9 times 9 plus 1 over 2. Okay, so that's going to be 5,050 minus 10 over 2 is 5. 5 times 9 is 45. Okay, so that would be 5,005. So this is an example of where I'm using the first summation formula, okay? Okay, right. Yeah, sure. Okay, so again, if I give you this sum here, and I ask you to evaluate this sum, okay, I want to use the summation formula number 1. The only issue is that I have to start at 1, but this thing starts at 10. So I'm rewriting it as the sum from k equals 1 to 100 of k, so that I can start from 1, and this way I can use the summation formula. The only problem is that if I just do that sum, I've got too much. I've added the numbers 1 through 9 to this thing, and I don't want those numbers. I want to start at 10, okay? So I have to subtract off the numbers 1 through 9. So I'm subtracting off the sum from k equals 1 to 9 of k. So anything extra that I added will be subtracted, and I'll get the sum that I want. Okay, now I can use the summation formula for both of those, and I'll get my answer. Sure, no problem. Any other questions on that? Okay. All right. So if there's no questions on that, then we are done with section 2.4. All right. Okay. So let's go back to discussing the schedule now. All right. So we're going to do on Monday section 2.6. We'll do all of 2.6, which deals with matrices. All right. For your quiz, I want to do a quiz on 2.3 and 2.4. You guys, some of you asked to do it on Wednesday next week. So if we finish section 2.6 on Monday, then next week on Wednesday, we can do a review and also have the quiz. Do you guys want to do that? And then the Monday after that would be our second exam. Okay. So the schedule that I'm proposing is as follows. Monday, we finish 2.6. Wednesday, we have a quiz and we do a review for the second exam. And then the Monday after that will be our second exam. Yeah, so that's what it's looking like. Okay. Okay. All right, so let's do that. All right. The quiz will be on 2.3 and 2.4. Okay. All right. All right, so 1 second, let me pull out the calendar here. All right. Okay. So today is November the 4th. Monday, November the 9th we'll do section 2.6. Wednesday, November 11th, we will have a quiz and a review day. And then Monday, November the 16th will be our second exam. Okay. So that looks like our schedule for the next 2 weeks. All right. Can I scroll back? Yeah, I can scroll back to equation 3. There you go. Okay. All right, so that's going to be the schedule. All right. Any questions about that or anything else from today? The second exam will be all of chapter 2. Yeah, the review will be on next Wednesday. Okay, we'll have a quiz and a review that day. No, we did not start 2.6. We have a couple of minutes left. We can actually start 2.6 now, or we can head out early today. Yeah, no 2.5. 2.5 is not in the syllabus. Okay. All right. Okay. So let's end here then. Let's end here. Let's do the attendance, and I'll see everybody next week. Can I go up where I showed summations? Back to the definition, I assume you mean? Yeah, I can do that. Okay, is this what you wanted? Okay, sure. Okay. All right, everybody. Take care. Oh, sure. Sure. Let me just. Scroll down. Here. Is that good? Okay. All right. I'm going to stop recording here.